Hey everyone, welcome back to the Embedded Systems Programming from Scratch series. In the previous videos, we wrote and compiled the C code to blink the onboard LED on the Arduino Mega by directly accessing the registers. We used the SRAM addresses 0x25 and 0x24, which we found in the datasheet. But the datasheet also provides two other addresses, 0x04 and 0x05, which are the I/O register addresses. The SRAM addresses we used in C actually come from these I/O addresses. In the ATmega2560, the I/O registers start at SRAM address 0x20. So if you add 0x05 to 0x20, you get 0x25, and 0x04 plus 0x20 is 0x24. In this video, we're going to use these I/O addresses directly in our assembly code to blink the onboard LED. In assembly, we usually use the I/O addresses directly with these instructions: out to write and in to read. If you want to use the SRAM addresses like we did in the C code, you would use STS instead of out to write and LDS instead of in to read. Both methods access the same hardware. While we can use the SRAM addresses, it's generally better to use the I/O addresses directly in assembly. The reason is simple. Instructions like out and in are designed to work with I/O addresses. They are faster and use fewer bytes. Using SRAM addresses with STS and LDS works too, but these instructions take more memory and cycles because they handle a full 16-bit address. So we'll stick with the I/O addresses when we're accessing registers like DDR-B and port B. Okay, let's bring the microcontroller to life using Asswmbly. First, let's define some constants at the top of our program. .EQU DDR-B, 0x04. .EQU port B, 0x05. And .EQU LED, 7. DDR-B and port B are the I/O register addresses from the datasheet. And LED is the bit number for the onboard LED. That's bit 7 of port B. Next, we need to tell the CPU where to start executing after a reset. And we do it like this. .org 0x0000 and RJMP reset. This line sets the program's starting address, and RJMP reset tells the CPU to jump to our reset label when it powers up. So this line ensures that our program begins at the right place in memory. Now let's define the reset label. This is where our program starts after a reset, and configure the LED pin PB7 as an output. And here we say reset LDI R16, inside parentheses 1 shifted left by LED, and out DDR-B, R16. LDI loads the value 1 shifted left by 7 bits into the register R16. Then out DDR-B R16 writes that value to the DDR-B register, which configures PB7 as an output pin. Here we create an infinite loop that will turn the LED on and off. Loop LDI R16, inside parentheses 1 shift left by LED, out port B, R16, and rcall delay _1s. Using LDI, we load the same bit pattern into R16 and write it to port B using out. That turns the LED on, Then we call our delay subroutine delay_1s, which we'll define later, to wait 1 second before toggling it off. Next, we'll clear the bit to turn the LED off. LDI R17, 1 shift left by LED. COM R17 and R16, R17. Out port B, R16. RCall delay_500 ms and our JMP loop. Let's break this down. Here in this line, we load the same bit value, 1 shifted left by 7 bits, into R17. COM R17 flips all the bits in R17, creating a mask that clears bit 7. And this line performs a bitwise AND between the contents of R16 and R17. The result is stored back into R16, which effectively turns the LED off. Then the out instruction writes it back into port B. And here we call a subroutine that will make the program wait half a second before repeating. We'll define that subroutine later. And finally, we jump back to the loop using RJMP loop to keep the LED blinking continuously. Now, let's start writing our 1 second delay subroutine. We'll begin by loading the value 4 into register R18. Delay_1s, LDI R18, 4. Next, we'll create a loop that calls the 250 millisecond delay subroutine 4 times based on the value stored in R18. Here we say D1_outer, RCall delay_250 ms and DEC R18 BRNE D1_outer and RET. Each time we call delay_250 ms, we decrement R18 by 1 using the DEC instruction. When R18 reads 0, the 0 flag set in the AVR status register is set to 1. The instruction BRNE, which means branch if not equal, checks the flag. If the 0 flag is 0, meaning R18 is not 0 yet, it jumps back to the label D1_outer and repeats that loop. Once R18 becomes 0, the 0 flag is set, so the branch does not happen. The RET instruction runs instead, returning from the subroutine. Execution then continues in the main loop, right after the RCall delay_1s instruction, specifically at this line. This gives us a total delay of about 1 second before the LED toggles. The 500 ms delay is similar. It calls delay_250 ms twice. Delay_500 ms, LDI R18, 2 and D2_outer, RCall delay_250 ms and DEC R18 BRNE D2_outer and RET. Now let's write the 250 millisecond delay subroutine. This delay calls the delay_1 ms subroutine 250 times. Delay_250 ms, LDI R20, 250 and D3_loop, RCall delay underscore 1 ms, DEC R20, BRNE, D3 underscore loop, and RET. And finally, here's our 1 millisecond delay. We're going to use nested loops and NOP. Delay underscore 1 ms, colon, LDI R22, 20, and ms underscore outer, colon, LDI R23, 230, and ms underscore inner, colon, NOP, DEC R23, BRNE, ms underscore inner, DEC R22, BRNE, ms underscore outer, and RET. For this delay, we're going to use two nested loops. This is our outer loop, and this is our inner loop. The idea is simple. We make the CPU execute a bunch of NOP or no operation instructions to waste time and create a delay. Here, we'll load R22 with 20 and R23 with 230. Since our CPU runs at 16 MHz, that's 16 million clock cycles per second, meaning each cycle takes 1 divided by 16 million or 62.5 nanoseconds. Inside our inner loop, each NOP takes 1 cycle, and since we have 2 of them, that's 2 cycles. The DEC instruction takes 1 cycle, and BRNE takes 2 cycles when branching or 1 cycle when exiting. So on average, each iteration of the inner loop takes about 5 cycles. In the outer loop, we also have a DEC, a BRNE, and the LDI R23, 230 instruction, adding roughly 4 cycles per outer iteration. So overall, we have 4 plus 230 times 5, and all of these times 20, which is 23,080 cycles. Now, if we divide 23,080 cycles by 16 million, we get approximately 1.44 milliseconds per delay, which works for this project. And that's it for this video. In the next episode, we'll take the code we just wrote, assemble it, and upload it to the Arduino Mega. I also walk you through how to create a makefile to automate the entire build and upload process so you don't have to run each command manually. You can find all the source files and code examples on my GitHub. The link is in the video description. Thanks for watching, and if you enjoyed this video, don't forget to like, subscribe, and turn on notifications so you don't miss the next part of the series. See you in the next one.